Okay, assignment 4, page 3. For any a bigger than 1, use induction to show that this statement is true, again, for any natural number, just like most of our induction proofs. Okay, so for this one, again, keeping in our typical, in our examples for this class, I'm only going to do the inductive step. So if we assume that 1 plus a to the k is bigger than or equal to ka for some k, then we're going to now try to show that this statement is true for k plus 1. So we will notice that 1 plus a to the k plus 1, and now the argument starts. So let's say, well, that's equal to 1 plus a multiplied by 1 plus a to the k. This is gorgeous because it brings us back to the inductive hypothesis, where I can now say that this is certainly bigger than or equal to 1 plus a multiplied by ka by the inductive hypothesis. And this yields, let's see, by distributive properties, ka plus ka squared. Now here's where we're going to have to do a little bit of sub-argument on the side, but it's not too bad because if you think about it, k is a natural number, so it's certainly bigger than or equal to 1. And then a was said to be larger than 1. So that would mean that whatever ka squared is, it shouldn't be much of a jump to say that you believe that this is bigger than or equal to a. In fact, it's probably strictly larger, right? Because when you're taking a bigger than 1, then when you square it, you're just going to get larger just from that piece. So it's actually technically strictly larger. But that should be a pretty clear truth. And what that allows us to say then is that this quantity must be bigger than or equal to ka plus a, which would allow us to factor out the a and say that that's k plus 1 multiplied by a, just like we need, because that's the statement up here, but with a k plus 1 substituted in. So sometimes, like with the trigonometric proofs, with the identity justifications, you can use the other side to think about what you need, right? I was motivated to try to get to here, but I really needed to find some way to do it straightforward and give an argument going straightforward. Okay. In the top right, it says use our special formulas and facts to find this sum. So in the first stage, I'll say that's the sum from 1 to 10 of k cubed minus 3 times the sum from 1 to 10 of k. By our facts, by our formulas and facts, the sum of the k cubes up to 10 would be 10 times 10 plus 1, which is 11, over 2 quantity squared minus 3 times the sum from 1 to 10 of k is 10n times n plus 1, so times 11 over 2. And so here we're getting 55 squared minus 3 times 55. And let's see, 55 squared is 5 times 6 is 30, 25. So 3025 subtracted by 165. So 5 minus 5 is 0. A bit of borrowing going on here. Gives me 6, and then 8, and then 2. So it looks like the sum is 2,860. Let's check that just to make sure. So if we clear this out, then we end up getting math sum x equals, go to 1 to 10 of the k cubed, and that's minus 3k. So yeah, 2860. Whew. Okay, next couple. Bees make a honeycomb by starting in a single hexagon. And then after they've started in that single hexagon, in the next stage they draw a hexagon off of the other hexagon. So at the first stage you have 1. Then in every subsequent stage you start adding on more hexagons going around. So you're going to have like 2, 2, 2, 2, 2, 2. So in that second stage you're going to end up having 2 times 6, which is 12, but notice how when I drew it, I overlapped the hexagons, so I'm going to have to subtract those 6 hexagons. So 12 minus 6 is 6. So in that second stage, you'll get 6 hexagons. Out into the next stage, you're going to now have rows of 3. So you're going to have 3 hexagons, 3 hexagons, 3 hexagons, 3 hexagons, 3 hexagons, and 3 hexagons. But again, notice how every time I double counted the intersections. So in that third stage, you're going to have 3 times the 6 sides, which is 18, minus the 6 overlaps, which is going to be a 12. And so hopefully you can start to see the pattern here now, but it turns out every time you're going to be adding on. So the next one's going to be 4 times 6, which is 24, but you lose the 6 overlaps. And now you can hopefully easily see the pattern, right? 6, 12, 18. The last one's going to be 24. So when we try to add these up, the 12 and the 18 are 30. The 6 and the 24 are 30. So we get a total of 61 honeycombs after that 5th stage. And for the final problem here, we have a collection of 64 math teams that are meeting for a competition, head-to-head single elimination, and after each round, half of the teams are eliminated. How many rounds and how many matches? Well, at the beginning, in the first round, there are 64 teams, right? After the first round is completed, you'll only have 32. So after round 1, you will have 32 teams left. After round 2, again, you lose half the teams, half the teams, half the teams, half the teams. And so after that 6th round, you'll only have 1 team left. So it'll take 6 rounds to get there. 6 rounds to find champ. So that is the answer to the first part of the problem. How many rounds will it take? For the matches, you can try to add up all of these numbers and see how many matches there are, but a really cool way to think about this is that there are 64 teams, and you need to have enough matches that everybody loses except for one team. And every time there's only one team playing one team and only one person loses. So the clear answer is that if you want to have 64 teams play, but you only want to have one winner, there must be 63 matches, right? Because you need to have 63 losers in order to crown your champion.